Hello, everyone. So I'm working on page 12 now, and we're still working with percent yield problems. Okay, so this is number 3 on page 12, and you're already looking at some work that I've already done on this problem. It's all pretty standard stuff at this point. I hope you see what I'm doing is being pretty understandable, and I hope that you understand what you're looking at right now. Just to work through this really quickly, we're given a certain number of grams of sodium bromide. We're given an excess of chlorine gas, and then we're going to make 12.8 grams of sodium chloride. Okay, what we need to do first is just find out how much sodium chloride we could expect to make. It's the theoretical amount of sodium chloride that we would get from our stoichiometry calculations. That all that is really doing is telling us how much we could possibly make. Okay, so I found out using these calculations that 45.9 grams of sodium bromide is 0.446 moles of sodium bromide. So going to the BCA table, all right, we know that we're going to we're going to use up all of the sodium bromide because we have excess chlorine. That means sodium bromide is the limiting reactant, okay? Even though we did not have to determine that. So in the end, we'll have 0 sodium bromide. It will all be used up. I did not need to do this calculation, but I just did it anyway, just to show you that it could be done. I filled out the entire BCA table, but all we really needed was to know the amount of sodium chloride that we could theoretically make. All right. Theoretically, we should be able to make 0.446 moles of sodium chloride. Let's see how many grams that is. Okay, so that gives us 26.1 grams of sodium chloride. How does that compare to the amount that we're being told that we actually made? We only made 12.8 grams of sodium chloride. So what's the theoretical yield? I misspoke there, by the way. We're trying to find percent yield. The theoretical amount that we should be able to make was 26.1 grams. We only made 12.8 grams. So that's a pretty dismal percent yield, honestly. That's less than 50% yield. But there you go. That is the answer to that problem. Let's try the next one. I can already see that there's a little bit more going on in the next problem because we are given the amount of both reactants there. If we're given the amount of both reactants, that means we're going to need to find which one is the limiting reactant. All right, let's jump into it. Okay, first, of course, since we're given grams, we have to convert to moles. You know by now that we can only use a chemical equation if we're looking at the quantities of stuff in terms of moles, right? Because moles is a counted number of things. And in this case, we're counting a certain number of molecules. So we've got 0.769 moles of sulfur trioxide, and we've got 0.622 moles of water. Let's see how this shakes out on our BCA table. Okay, starting our BCA table again, we're given both reactants. We're given the amount of both reactants. So we've got to determine which of these is the limiting reactant. All right, now I'm looking at this and I can see immediately that we're going to use up all the water before we use up the sulfur trioxide, right? So here, I'm going to fill this out in real time. So we're going to use up all the water. And if we're using that much water, we're going to use that in SO2 as well, because this is a 1-to-1 mole ratio. For every 0.622 that we use of water, we're going to use 0.622 of SO3. So let's just see what the excess. All right, we're going to be left with some excess SO3. This will be the number of moles of SO3 that's in excess. We won't have any water left over. And in the process, we will make 0.622 moles of H2SO4. By the way, that's sulfuric acid. Let's see how many grams of sulfuric acid that is. All right, so running that calculation, 0.622 moles of sulfuric acid is going to be 60.96 grams of sulfuric acid. Let's see how that compares to the amount that we actually made. Okay, we actually made 54.9 grams. Okay, and there we have it. That comes out to be about a 90% yield. So there you go. Let's try the next one. Looks like this next one is going to be pretty easy. So I think I'll just work it out, and then I'm going to show you the results, and then we can talk through it real quick. All right, so I worked out this problem. It's pretty simple, actually. First, of course, I calculated the number of moles of ammonia that were given. And I put that into our BCA table. Now, it's especially easy because we've got a 4-to-4 ratio between the reactant that is limiting, which is the ammonia, and the product that we're interested in. We're interested in the amount of NO because that's what we're being asked about. Nobody's asking us anything about the water. So I just left the stuff out of the calculation that is not necessary for the calculation for this one. We would make 0.93 moles of NO if we were to use up 0.93 moles of ammonia. So 0.93 moles of NO, that turns out to be 27.9 grams of NO. This, of course, is the theoretical amount that we could possibly get. All right. Take the amount that we actually made, 21.8 divided by 27.9, and we're getting the percent yield. So we have a percent yield of 78.1%. All right, I am going to go on and solve the next one. For the next one, we're going to need to actually write out the chemical equation. But essentially, these are all the same now. I mean, we're just calculating an amount of material that we can make. We compare that amount of material to the amount that was actually made, and that's the percent yield. I will work this out really quickly, and I'll just show you the answer, and we can talk through it real quick, and then that'll be it. All right, first off, we need this balanced chemical equation. This is the balanced chemical equation. I don't think that I made a mistake there. So we'll push forward from here. So we're given an excess of oxygen. I need to know the number of moles of, this is what, antimony sulfide. Okay, great. I'm going to find the number of moles that is, and then we'll march forward. All right, here it is all worked out. I found that we're starting with 0.29 moles of the antimony sulfide. Okay. I only filled in the BCA table with what we actually needed to solve the problem. So using all of the antimony sulfide, the mole ratio is 2-to-1. So for every 2 of the antimony sulfide, we will make 1 antimony oxide. Great. Okay, so we're going to take half of this number, which is this number. Okay, we're going to make 0.145 moles of the antimony oxide. All right, what is that in grams? Well, this is the molar mass, and doing the calculation, we find that we should be able to make 84.6 grams of antimony oxide. That is the theoretical amount. Okay, taking that theoretical amount and comparing it to the amount that was actually made, we've got an 85.6% yield. All right, so that should do it. I will continue with some more videos if you still need some extra help.